the solution for the quiz, so you can check. There's a little bit of a mistake on the beginning of the video, but I think just that one question. And you can also check the PDF file for the quiz solution. And if you have anything to discuss about the quiz, the first quiz, you can email me or maybe chat me through the Moodle. That's also okay. All right. Today I'm planning to finish the chapter 3. So hopefully I can finish chapter 3 by today, and we can move to chapter 4 next week. Or maybe today we can briefly get into chapter 4. Okay. Okay, hopefully you already scanned the QR code. Okay, let me give you maybe 1 minute. Okay, now we can start our course, and let's start with the feedback for last Tuesday. So we have this statement here. The correct statement should be 1 minus x squared. Okay, this is the correct one. So this statement here will be false. Okay, so yeah, majority of you got correct answer. Okay, so that's okay. Okay, the second question, you are given this equation here, tangent inverse, and then x squared. So the idea here is to implement the inverse trigonometric, and then using chain rule to solve. So tangent inverse becomes 1 over 1 plus x squared and then squared, because the tangent inverse, if you remember, this will be 1 over 1 plus x squared. Okay, so when you change the x with maybe x squared, x cubed, it will goes to here. So you will have 1 plus x squared squared. Okay, or if you have cube, you can have cube like that. Okay, so you have this y prime. Okay, and then y prime at x equal 1, we just plug in 1, and then that should be equal 1. And I think, yeah, most of you got the correct answer. Okay. Okay, the last question, if you look here, I have this equations, y, x tangent inverse minus half ln, and then 1 plus x squared, right? Okay, the question is to find the first derivative. Okay, how to find the first derivative? We can first look at x tangent inverse. We can derive this by product rule. Okay, by product rule, and then using the inverse of trigonometric functions derivatives, we get this will become tangent inverse x and x over 1 plus x squared. Okay, and then the second equation here, the half ln, we can differentiate ln, and we can write 1 over 1 plus x squared, and then chain rule 2x. Okay, multiply by 2x here, 2x. And then 2 will be canceling with this, and this will be resulting the same element as this one. So we can cancel this both. We cancel this, and we are only having the tangent inverse x as our answer. So that will be the result, the tangent inverse x. Okay. So this is tangent inverse x. So yeah, congratulations for the winner. Okay. Okay, now before we are going to the next section in chapter 3, let me just give you a brief, or maybe some example, another example on First is this. It's from the textbook. We have a Ferris wheel. It has radius of 10 meter. It's rotating at a rate of 1 revolution every 2 minutes. How fast is a rider rising when his seat is 16 meter above ground level? Okay, so first you need to know what this question is about. Okay? First is Ferris wheel. Okay, if you don't know what Ferris wheel is, it's like when you go to the amusement park, you will see that there is, or maybe let me draw a circle like that, and uh, and this this is having rotated, right? And then usually you are taking maybe some ticket here, and then you are get in line. You get one by one, or maybe one this one box here, maybe 4 to 5 people, maybe, right? And you get in. You are going up, right? The Ferris wheel will takes you to the some height, okay? Maybe this some height like that, and maybe you take some photos from this height, right? And I think you can view most of the amusement park. You can see from the top, right? So this is the Ferris wheel. Okay, I hope you are familiar with this. Yeah. So the radius is 10 meter. So let me maybe mark this in terms of the radius is 10 meter. Let me just write this 10 meter. The radius is 10 meter. It's rotating at a rate of 1 revolution every 2 minutes. Okay. So you need to understand what 1 revolution means. So 1 revolution means this is a full circle is 1 revolution. Okay. So let me write 1 revolution means full circle. And we know that full circle means it's 2 pi. Okay. So 2 pi, we can say our rate of change of our angle with respect to t is 2 pi radian, okay, divided by 2 minutes. Okay. Or we can say that this is pi radian per minute. Okay, now there's some still you need to understand how the question is, right? So how fast is a rider rising when his seat is 16 meter above? So we need to maybe making some picture when does the uh, the seat is when it is when the height is 16 meter above ground level. So maybe let me draw another one here. Okay, let me draw another one with maybe just a circle. Okay, now it's say that it has 10 radius. Okay, let me write 10 meter, and let's say this is our height here. So the height is in total should be 16. 16 meter above ground level. Okay, so here's the ground. So this will be 16 meter. So we will have, if you draw here, then we will have a triangle here that is precisely 6 meter. Okay. So we have 10, 6, right? Okay. Now we have, if we have this this triangle here, if we have this, then this part will be 8 by Pythagorean, right? Or let me write here. So this will be 8 meter. And if the angle here, okay, so if the angle is here, then we can write the cos theta is 810, sine theta is 610. So the question is actually asking how fast is a rider rising when his seat is 16 meters. So let me write this, maybe not 6 meters first. Let me write this in h first, so you understand what the question is. Okay. So this is h. So we are actually looking for dh dt. Okay, dh dt at h equals 6. That's actually the question. So hopefully you understand the question. And then from all the figures, when you have h equals 6, okay, so when h equals 6, you have cos theta is 8/10, and then sine theta is 6/10. Okay. If you look with the triangle with h, so if you have h and 10, because 10 is a fixed number, okay, imagine this, the radius is always the same. So we can have sine theta relation with h and 10. That is our relation there. And we can simply differentiate this part. Okay, we can differentiate h equals sine theta, or 10 sine theta. Okay, and then we can write this. And we can simply start to write dh over dt. And then 10 sine will be 10 cosine theta d theta over dt. Okay. Now, cos theta is 8/10, and d theta over dt is pi. So you will get directly this will be 8 pi meter per minute. Okay. Let me give you the whole screen like that. I think this should be enough to answer. You want to completely, maybe here. Okay. Okay. Okay, hopefully you guys can understand the concept here. Okay. Okay. Okay, let me continue a little bit. So this is about the Ferris wheel. Okay, next question. Okay, next questions. I've prepared there's a plane flying with a constant speed. Okay, this is a little bit you need to carefully read. Okay, so there is a plane. It's flying with a speed of 300 kilometer per hour, and it passes over a radar station. So it's passed away. This the plane, and it has altitude of 1 kilometer from the ground to the height of the plane. Right? And then the plane itself, it's not going horizontal. It's going climbing at some certain angle of 30 degree. So it's asking at what rate is the distance from the plane to the radar station increasing 1 minute later. Okay. So first you need to draw the diagram. So you have the plane, you have the radar, and you have some quantify, some numbers that you are going to put on, and then you need to calculate the rate between plane and radar stations after 1 minute. Okay. Um, Actually, the result is not really in a good number, so it is. I think you need to use some calculator to solve at the end of the results. But first, you need to draw correctly to get the solutions. Okay. So first, we need to draw at least the illustration how the situations. Okay. So first, a plane. Okay, let me draw a plane. Okay, a plane flying with a constant speed. Let's say this is his the this, how the plane is going on. It passes over the radar station. So let's say this is the radar station, or maybe the radar station, right? Like that. And it has an altitude of 1 kilometer. Let's say just one, okay? Because all the units will be kilometer in kilometer. So 1 kilometer. And then it's, let's say this is x, okay? This is x. So dx over dt is 300 kilometer per hour. But it keeps increasing. Oh, I need to make it a little bit lower so that you can see that it has some certain angle. So it climbs at an angle of 30 degree. So this is maybe climbing like that. And it has, this is 30 degree from here. Okay. Now imagine the plane now is going to be here. So this is A, this is B. So the plane is going to be evaluated at B. Okay. Now we have, this is, let's say this is R, the radar. Okay. So we have R, A, B, and that become our clue, our triangle, right? Our triangle. So we have Okay, let's say that's our triangle there. And let's say this is A, B, and R. This is 1. And let's say this is X, okay? Maybe a better X is the distance here, okay? And will be Y, okay? Well, if you want to use another symbol, that's also fine, but I will stick with X and Y for this one. Okay, now this is 30 degree. Now the whole thing here, it's become 120, right? 30 plus the 90 degree, so it will be a 120. Okay, now you have sides 1, X, Y. You have all 3 sides and 1 angle. You can use some formula for triangle. I believe you still remember, but if not, let me write down for you. We have law of cosine. Let me introduce you to the law of cosine very briefly. I hope you don't mind. So if this is A, B, C, let's say I think this will be A, B, and C. Oh, let's just maybe. Let's just say this is angle, angle, angle. So the capital C, capital B, capital A, let's say that's our angle, okay? If we want to make it in terms of C, let me write C squared, A squared plus B squared minus 2AB cosine C, okay? Want to write B squared, A squared plus C squared minus 2AC cosine B. And if you have A squared, you have B squared plus C squared minus 2BC cosine A. I hope you still remember this this expression here for law of cosine. And then we have now x, y, and 1. So let me just write in terms of y first, and then 1 plus x squared minus 2x cosine 120. Okay, and then we can write this as y squared equal 1 plus x squared minus 2x, and then cos 120 is minus half, okay, minus half. And then we can write this as x squared plus x plus 1. We have this expression. Let me put this a little bit right here, and here will be a little bit here. And let me resize this to make it a little bit smaller. Okay, so we have y squared, x squared plus x plus 1. Let's differentiate all with respect to t. So we have 2y dy over dt, 2x dx over dt plus dx over dt. And we have expression for dy dt, the distance between the plane and the radar. Is we solve this, and this will be 2x plus 1 over 2y dx dt. Okay. Now the question is asking after how much? Oh, a minute later. Okay. So we know that 300 kilometer is for 1 hour. So for 1 minute, we have it's 5 kilometers. So we are using this 5 kilo as our calculation here. So x will be equal 5. When x is 5, then y will be, we can use it with the this expression here. So y squared is 5 squared plus 5 plus 1 is 25, 5, 31. Okay, so y will be square root of 31. Now we can put here 2, 5 plus 1, and then 2 square root of 31, and the x over dt is 300. And if you want, you can solve this, and this will be around 1,650. Not really a good number, and I don't like the results, but this is the results. Okay. 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 Any questions? Yeah, usually if the questions having the law of cosine, usually they will have not really a good structure in the number. So it will have a square root, like this one is having square root of 31. So that is not really a good number for the questions. Okay, any questions? Okay, I think I will have the teaching assistant give you maybe 2 or 3 question, or maybe 4 questions for your TA session for solving the related grades. Okay, hopefully you can uh, have better understanding for solving the related rates. Okay. But still, the idea for related rates is first understand the question, where the question is going on, and then try drawing in the diagram. Okay, until you get the idea how to connect all these numbers. Okay, so actually to get into the idea on this triangle here and using law of cosine, you need to take sometimes. Okay, if you get the idea already, it will be very fast, right? But if you take some time to think how we can connect all the numbers, all the situation into the triangle, and then directly connect to law of cosine, that you need it takes time to get in there. Okay. Okay. Any question? If not, I will continue for the next section. So we will leave the related rates, and hopefully, if we have time to review for next week or next 2 week, I will review which are more uh, necessary for you, or maybe we have some examples, maybe 30 or 40 minutes example for another day if we have time. Okay, but I think we can leave it for now. And this is 3.9 related grades. The next section is 3.10. It's about the linear approximations and differentials. We have 311 hyperbolic functions that we will skip. We will skip. Why we will skip the hyperbolic? Because I think hyperbolic how we are going to use the hyperbolic is actually similar with what we have in the trigonometric. So I think maybe I can give it in an additional video, but I think I will not add the hyperbolic in our curriculum for this semester. Okay. Yeah, I believe too much content for now, so I will skip that for now. So we will go to 3.10 linear approximation. I will get into that. Okay. So linear approximations. Okay, linear approximation. So this is 3.10, and once more, I announced that 3.11 I will skip. Okay, this is hyperbolic function. This will skip. Okay. So 3.10 linear approximations. Okay, what are linear approximations? So the idea for the linear approximation is actually how we can use calculus, at least, to be applied when you want to approximate some value. Okay. Okay. For example, you want to know some difficult calculations, and then you want to approximate with the tangent line. Actually, that is the linear approximation means. Okay. So for example, okay, let y is equal f of x. Okay. And you want to evaluate at x equal a. And at x equal a, if you want to evaluate the first derivative, or f prime a, okay, this is at a, okay, f prime a, you know that this is actually our limit, right? We can write our limit like this, you remember? Or you can also write the limit with h. Okay, but let's observe this form here. If you are using the limit here, meaning that it's actually the real number here is not exactly the same as our f prime, but it's closer, right? The term's limit means closer. So we can write, this is more or less, or approximately, right? Approximately, this is the same. Well, not exactly the same, but it's close to. Okay. If you try to solve this, to find f of x. So let's solve this. Okay, and we can solve this, and this will be our solution, right? So we can rewrite our tangent equation, and we can make it into this equation now. Okay. So why we are doing this? Okay, so going to the graph. Okay, now you have this graph here. This is y equal f of x. Okay, and you have a point here, which we are already discussed, that this is x equal a. We want to observe at this a, there will be a tangent line. The red line here is the tangent line. Okay, let me write here. This is the tangent line. Okay. Okay. That's the tangent line. So what's so important about this tangent line, and why it's unique, and why we can use it to approximate some value or some number? Okay. So when we are looking here, and we have this y, right? We have this y equal f of x. This is with some, this is a tangent line equation. Let's say this is our equation here, linear equations, like, right? If we look at from here, it has a gap, right? It has a gap. And then if you remember the limit, when you get close to the number a here, when you are getting closer here, the gap is getting smaller, right? It's getting smaller. Okay, that's first thing. So when you look here, eventually, because my paper or my notes here using some limit for, it has some limit in the pixels, right? You cannot see any difference here, right? Maybe here. It seems that red and blue are in the same line and maybe the same equations, right? So when we are going to evaluate a number nearby a, we can have, and we can approximately, seemingly, that our functions is this. We have this kind of linear equations. Okay. Okay. So for example, if your a is something that, let's say the f of x is square root of x, and our a is maybe 4. It's easy to be evaluated, right? But when you have maybe b, b is 4 point maybe 0.1, or maybe not 0.1, maybe 4.1. It we can have some approximations, because we know that we can have a that equal 4, and then we can have some delta of x that we can use for, and we can apply to our equation here. So we can have, this is the delta x. We can have this is f 4.0 4.1, and we can have the f4 plus f prime 4, and then we can multiply with the delta, and it become easier to be calculated, right? So you just need to calculate. So you have the f prime x, and you have the f4 is of course 2, f prime 4 is the 1/4. So you'll have f 4.1 is getting closer, or approximately will be 2 plus 1/4, and then the delta will be 0.1, or you can say 2 plus 1/40. And if you check with calculator, maybe the result will be close to this result. Okay. And then when you have more and more the delta getting more 0 like that, you will have more precise results, and it will be getting closer to the 4. And later we will know that we can have some error in our calculation, and we can set how many errors that we want to have, how many percentage that we want to have, and that will be using the same applications, the linear approximations. Okay, I hope you get the feeling, you get the basic idea. Okay, so here's we call this also linearization. What linearization means is you have a functions, and you want to observe at certain point and make that functions equal to linear. Okay, so you cannot have a number that is really maybe not close enough. Maybe you want to observe a number here, this maybe x equal b here, it's too far, and the gap between the functions and the linear at a is it's too wide, right? So you cannot use that. So you only can use the number that is close by a. Okay, or you can also write in terms of this. Okay, it's actually the same thing. It's actually the same thing. This is for approximation. Okay, but this is the linear equations. Okay, the linear equations, similar but a little bit different, but actually the concept behind these two is the same. Okay, okay, let me stop here for now, and give you some time to write first. Okay, let me give you another simple example to get into the linear approximation. Okay, if you want to find, for example, okay, find 9.0106 using calculus. Well, if you want to confirm, you can check with your calculator whether it's correct or no. Okay. If this is just this question, then first, how to apply the linear approximation? First, you need to define the function. So first, define the function. So let me write here, define the functions. Okay. So here we just have square root of something. So probably we can just use the square root of x, okay, which we already used in the first example in intro. And then second, find the derivative. Right? And then you have the formula for the linear approximation. And this is the formula. Okay, now pick A, choose A. Okay. If x is 9.06 and f of x is square root of x, the ideal A should be 9, so that you know that fa will be square root of 9, which is 3, that you can easily calculate. Okay, okay, that's how it's going. And then evaluate all the things here. So f of the number that we want to evaluate, this will be f of a. F of a is 3 plus f prime a. This will be 1, 2, and this will be 1 over 6. Okay, and the delta will be 0.06. Okay. This will be resulting around 3.01. And you may see that if you try to multiply with this, you will have 90601, which is close by 906. You have another term here at behind, and this will be determining how perfect the calculation is, or is there any how much error you have. Okay, and the terms error, you will understand that will be determined by how much decimals behind the number. Like for example, you can also have 9.0600000001 maybe. So it's much more better than this 01 here. This is better than this, right? Okay, but it's still closer to what we are going to find. Okay, and sometimes this plus and minus here, sometimes it's makes some confusion, especially okay if you see here it's 9.06. It's your a is lower than your x, right? But you can have a is greater than x for also, and you need to be careful when you put plus and minus because you will get the wrong answer. But if you are checking your answer carefully, you will notice the logic behind it. Okay, so for example, like this one, your answer should be around 3 something bigger than the original 3. Okay, let me give you another example. Okay, let me give you another example, or let me just briefly stop here to give you some time to check. Okay, if you have any questions, you can also asking me if you want. Okay, so with this method, linear approximations, you can approximate some value or some, if you know the functions, you know the derivatives, you know how the tangent line will be, how the linearization will be, you can evaluate some value with choosing some x nearby the tangent line point. Okay, now that's we call linear approximations. Okay, still related to linear approximations, actually, if you read the sections on your textbook, if you have textbook, somewhere in chapter 4, you will notice that you have another method. It's called the Newton's method. Okay, but I want to show you that it doesn't need to be really complex or complicated, because it's actually using the same principles. Okay, I show you how. Okay, I show you how, and this is actually in chapter 4, but I will put here for a brief to see what's the connections, because it's really connecting with the linear approximations. Okay, so first is, if I have an fx like that. Okay, let's say this is f of x. Okay, this is f of x, and maybe I will put some point here. Let's name the point x0. Okay, at this x0 here, I will have a tangent line right here with that red line. Okay, so let me start with this. Remember that f prime a will approximately the same or getting closer to this expression as we have done before here. Okay, this expression, right? Okay, now the idea here is we want to know, okay, we want to know what we are going to do in Newton's method is actually we want to find this x here, or we want to find the roots in the functions. So this is our goal. Okay, let me write here. This is our goal. Okay, so how we are going to get this our goal? Okay, so if we have the tangent line, we know that if we have this x0, we put the tangent line, and the tangent line is crossing this x, right? Crossing here. And you see this getting closer, this distance. Sorry, this distance is getting closer, right? Getting closer, right? So why we are not using this x, another x here? Let's say this is x1, and make it until here. Okay, and make another tangent line. You will notice that when you do that, there will be another tangent line. The tangent line that cross x-axis will be getting closer to the roots. Okay, so instead of finding in linear approximation, you want to find f of x, right? You know the x, right? Let me write here so you can have better understanding. In linear approximation, you know the a. Want to find f of x, right? Equals something, right? But in Newton's method, you know f of x, want to find the roots, which is the x or the a. Okay, Now let me write the expression one more here, and let's solve this and find or get into expressions for x. Okay, so to find roots, we need to have f of x need to be 0, right? F of x need to be 0 to find roots. So this will be equal or approximately this. And we can cross multiply. F prime will be here. Okay. And now we have x is a minus f of a and f prime a. And how we are going to deal this with the graph here. So our x0 is actually our a. So let me change all with x0. So x, let's say x1, okay. This is x0 minus f x0 f prime x0. And then if you want to calculate more and more closer to the roots, you can go to calculate x2, which is x1 minus f x1 over f prime x1. And if you are getting, maybe you still need more calculations, maybe you want to have like 3, 4, 5 times calculation, you can have until as much as you want, depends on you. Okay. That's a little bit about the Newton's method. But I will not describe or elaborate more than this. Okay, I will describe later on chapter 4. But this is to keep in mind that actually the method is based on the same principle as the linear approximation. Okay, so I think we can move on to chapter 4. But before chapter 4, I think I can give you some. Okay, anyway, any questions first? Any questions? Okay. Before going to chapter 4, maybe some symbols that I need to give you. Okay, let me go here. This is called the differentials. Okay, so before we go into chapter 4, I forgot to give this differentials. So differentials is actually, it's just a terms, okay, a new terminology. So y equal f of x. If f is differentiable, then differential, let's say dx, okay, is independent variable. Differential dy then define in terms of dx. Dy equal f prime x dx. So we can say dy is dependent variable. Depend on x and dx. And how we are going to interpret this statement here is basically by looking at the graph here. So if you look here, we have a functions f of x, and we have the a tangent, the red line there, and we can have a difference in terms of delta x and terms of the actually delta y, the actual functions. But if you look at the tangent, we will have this delta y here. And the dx is basically, it keeps the same here. Okay, so the geometric meaning here, the corresponding change in y, this will be delta y is fx plus delta x in f of x. And slope PR is the derivative. Okay, so delta y represent how much the curve f of x rise or fall when x changes by amount of dx. Okay? I hope you get understand. Okay, this is just the terms that so whenever we are using differentials, this equation here should be in mind. Okay. Well, it's actually it's the same, or it's pretty similar with what we have in derivative, which is dy over dx. This is our f prime x, and actually we can also have similarities. Okay, but differentials, it can be applied to more general engineering. Okay, and whenever you find d something blah blah blah, d something blah 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 in physics, in chemistry, you know that when they put the equation like that, this means this is differential equations. Okay, differential. Okay, you will use it again in the I think in physics, in advanced mathematics, in engineering of math. You will see this differential terms again and again. This is just the terms. Okay, I hope you get the point of all this. The idea is just still same: tangent line, the slope, the difference between the height. Okay, that's the differential meaning. So you will notice the difference of y when you change the x, or the amount of x. Okay. Okay. I think that's it for the chapter 3. Okay. So chapter 3, we'll say chapter 3 finish. So maybe 1 or 2 weeks from now, be prepared for the quiz. Okay. So only chapter 3, only derivatives. Okay. But now I will move to chapter 4. Okay. I hope you don't mind moving to chapter 4, and I will let your TA to prepare you in chapter 3. Okay, so you can have more exercise. If you have, like, maybe you still have some discussion on some questions, or maybe some problems, we still have some TA preparations for you that will be prepared for the quiz. Okay. Okay. Now, I will let you go to some physics first. Okay, some physics, but it will relate to what we are doing later. Okay. Do you still need to take notes here? I think no, right? Okay, I can move. Okay. If you want to write this note, let me know. Okay. Okay, let me go through some physics. Okay. And I believe this is just easy problem for you. Let's say we have a function, like a distance functions, displacement functions. This is t cubed minus 6t squared plus 90. So this will be a distance, or maybe position. Okay, if you were asked to find the average velocity and average speed, what is the difference? If we want to evaluate from t equals 0 to t equals 5. So what is the average velocity? What is the average speed? Two different case. So we need to look at this case first. Okay? And then later I will let you know why we are doing this and what is the connection with the chapter 4. Okay. Okay. Now let's start with the average velocity. Okay. Average velocity. Average velocity means this is just to let the calculations only restrict the change in position over the time interval, right? While the average speed is the total distance traveled over time, right? Or total time, or time interval. Okay. If we are looking at these questions, let's say we are going to compute the average velocity. Let's say this is our velocity. This is S5 minus S0 divided by 5. Okay, S5 we can check here as 5 cube, it's 125, 25, 6 plus 9, 5. 9 minus 25 plus 45, it's 20, right? Okay, so it's 20, 20 over 5. This will be 4 meter per second. Okay, now let's see the average speed. It's the total, and let me write one more. Total distance divided by time. Okay, now we are looking at these equations, right? T cubed minus 6t squared plus 9t. Okay, if we are going to evaluate this, the average speed, we know that if we differentiate this, we are going to have some rate of change, okay, of s with respect to t. Let's say this is 3t squared minus 12t plus 9, okay. And we can also write this as, let's say we can write this as t squared minus 4t plus 3. We can factorize this. We can have t1 and t3, which is equal, if we want to equal it to 0, what 0 means here? What 0 means here? Okay. If we're going to draw the line, okay. This is t equals 0 here. Maybe you are here, okay. And then t equal 5 is here. And of course, at t equal 5, you're having s in meter. Okay, I forgot to mention that. So when you are 0, this is 0, 0 meter, okay. And then t equal 1, let's say t equal 1 here. When t equal 1, this is minus 6. 1 minus 6 is minus 5, plus 9 is 4. So this will be 4 meter. This will be 4. And then when t equal 3, okay, when t equal 3, what is the number 3? 27. 27 and 36 is negative 9 plus 9 is 0. Okay. So what is happening here? So you are going forward. You are going forward first, okay? And then you can also check if you want to check the S2 if you want. 2 will be 4, 3, 12. 12 minus 24 to negative 12, negative 3. Or 3, negative 12. Yeah, 12, negative 12, yeah. So it's going way back, right? So You get here, and then instead of moving forward, you're going back. Okay, you're going back. That is t equal 3 there. And then suddenly this is 2. And then suddenly you are going to t5. Okay, so the average speed is 4 meters, and then turning back 4 meters. So 4 plus 4 plus 20 divided by 5 seconds. Yeah, 5. Yeah, t equal 5, right? So this will be resulting 28 divided by 5. This is 5.6 meter per second. So what is really happening here? So if we look at, if we have a graph, okay? Remember, when we are dealing with the rate of change here, we are dealing with the slope, right? We are dealing with the slope. The slope, when the slope is 0, which means they are having probably here. Okay, let's say this is the random function. This is just to illustrate. This is when slope is 0. Okay, so you have increasing. It is positive slope, but when you are getting nearby the extreme point here, the point here, you are actually getting decrease, but not turning the positive into negative. So it's still positive, but it's still decreasing. Or if you remember, if I draw the slope is going to be more horizontal. And then after 0, you will get the slope is negative, right? It's negative. There. This we call also, this point is our turning point, which is precisely what we are looking at here. This t equal 1 and t equal 3. What's happened on t equal 1 and 3? So you are moving forward here, and when you are reaching this 4 meter, you decide to going back. Okay, so you decide to going back. Let me write here. Let me draw and make it going to the left there. So he is going to the left, and when you are having reached t equal 3, you then move again to the right. Okay, so this t equal 1 and t equal 3, we call this is our turning point. And because if you look at the graph or the curve, t cubed minus t squared plus 9t, I believe you already guessed the graph, which is it has a cubic formula that you can, maybe it can be like that. So you have this and this as your slope. Okay, so you can have positive, or maybe not really like, maybe like this. Yeah, maybe that's more logic, right? More reasonable, I think. Here and here, so you have a turning point. Maybe this is 1, this is 1, and this is t equal 3. Okay, now we are going to elaborate this graph here in chapter 4, and we are going to name this is our extreme point, or local, or you can have the name local max, and when you have down like this will be local mean, and we also have the absolute max, absolute mean. And this turning point, we call this also a stationary point, or the important one, this is called also critical point. I think in the textbook you will notice the critical point more than the turning point or stationary. Okay, now let's going to deep forward here. Let's move forward to chapter 4. I hope you get why I wrote this physics problem to you, to get to the idea why we are doing the chapter 4. Okay. Do you still need to take some notes here? Let me give you maybe a few minutes to think, or maybe to write some notes. So after the course finish, I will collect all the chapter 3 notes, my notes, and then prepare it to you guys. All right. I have around 5 to 10 minutes left. So this is just an intro for chapter 4. Okay. Chapter 4 is started with 4.1 about maximum and minimum values. But before maximum and minimum values, my preference, I will start with mean value theorem. You will know why. I will you will know why later. Okay. So mean value theorem. What is mean value theorem? So first, let me write the theorem first. We suppose a function is continuous over and a function's differentiable. Okay. Okay. You notice that I write different interval. The first one is having the closed interval like that, and the second one is having the open. I hope you know why. Okay. I hope you know why. Do you know why? It refers to the continuity and the differentiable things. Okay. If you have a differentiable function, it should be continuous, right? But if you have a continuous function, it's not always differentiable. That's why I will write the differentiable not include a and b, but just saying that there is something that differentiable between a and b. But if continued, it will include the a and b, okay, to be involved. Okay. All right. There's Rolle's theorem. Okay, so there's called Rolle's theorem. Yeah, Rolle's theorem is this, and the other definition is there will be this this consequence, or we can say that there is a number c in a b such that f prime c, or such that this, okay, or we can write also in terms of this. Okay, notice that the same idea with the linear approximations, the same idea with our derivatives definition, we now have similar idea, and we call this as the mean value theorem. Why we call it the mean value? Because or let me write here first the definition here. So there will be A less than C less than B. Okay, we can actually write C, there exists C whose average rate of change is equal to instantaneous rate of change. Okay, what does it mean? Okay, here I have a random function like that, and I have the second line here. This is A, f of A. This is B, f of B. Okay. Now between A and B, there will exist a tangent. Let's say here. The tangent is here. So let's say this is our C. So this is what we say. This is the secant. This is a tangent. So average rate of change is our secant. Our instantaneous rate of change is our tangent. Okay, I hope you still remember that definition. Okay, and the mean value theorem is saying that there will be f prime c, the tangent at C, will be equal with fb minus f of A divided by b minus A. So it says that, okay? Or maybe here also another C here, right? This is also, we can say that this is C that is possible for the C, right? We have F2 there. Okay. I think I will stop here, okay? And then I will continue from here. What is the consequence? And that is why we have the maximum and minimum value. So we are going to start with the mean value theorem first, okay? I have a different approach from the textbook, but still okay. The textbook still okay, but I want to start from the mean value theorem and then going to minimum value, maximum value, because all the minimum value and maximum value came from this mean value theorem. Okay. Okay, let me give you some time to think here, and we can start our feedback time. Okay, for today. And thank you for joining the class. I'm sorry I cannot come into the class because I still feel, actually I feel better today, but yesterday I feel not comfortable. Okay, if you finish this, then we can go to our feedback time. Actually, the feedback I prepared is actually related rates. I want to know how you can handle the question from the related rates problem. Okay. Okay, let me start the feedback time. Okay. Okay, this will be about the related rates. If you have, but I already prepared the number to be not too complicated or not too difficult to be calculated. Okay. Yeah, actually the vaccine effect is sometimes makes me feel dizzy. I don't know why, but I think every person will be different. Yeah. Okay, and I hope the time for each question is enough. I think I checked the time is 2 to 3 minutes each questions. I hope that's enough. Okay, let's start. Okay. Okay, anyone want to join? Okay, 23. Okay. Uh, I believe it's if you are using your real name and student ID. At the end of the semester, I will check who will join, and maybe I will have some considerations for your maybe some bonus point for all who join, not only the winner. Okay, not only the winner. Okay, 3, 2, 1. Let's start. Yeah, even 4 minutes for this question. I hope enough. If you confused, altitude mean height. The height. Okay. And you just write the number. Okay, write the number in decimals. Okay, 20 seconds. Okay, also check how much time you need to finish the questions like this. 3, 2, 1, yeah, just random answer. Yeah, 1.6 or 1 with negative is also correct. I put the answers. Oh, yeah. 1.6, yeah. Okay, sorry if you write with the comma. Okay, I should prepare the comma answer. Okay, sorry. Okay, who are... Okay, congratulations, Nick. Okay. Okay, next question. Okay, 3, 2, 1, let's start. Okay, I prepared the A, B, C, D. Okay, 30 seconds. I think the time is okay. Okay. Oh, okay. Okay, I will maybe give you some review later on the next class. Oh yeah, still Nick, you got the highest score. So congratulations, Nick. And that will be the end of our course. Thank you for joining. And sorry, I cannot come to the class. I still feel a little bit dizzy, but it's better than yesterday actually. Okay, so yeah, that's conclude our lecture. Anyone need the QR code for the attendance or no? If not, then we can finish our lecture.